large-scale fields. And for the beginning, I just like present some other simulation of what other people are doing. Like there are people doing like looking at flux emerge, like how magnetic field emerge from the convection zone photosphere. But important thing is they don't go very deep down and they don't go very high up. And here also you see, and they're not generating the magnetic field by themselves, so they just put it in. And some other thing is flux tubes. There are lots of simulation, lots of people doing simulation on flux tubes. I don't know if you know all of this, the model. Like one of the main models to explain sunspots is that you have a flux tube forming at the tachoclide, at the convection zone, and it will rise up to the surface. And when it go through the photosphere, you get like two sunspots with the opposite sign. But okay. But flux tubes have some problems. So when some people doing here flux tube simulation, rising of the flux tube, sometimes they get destroyed. And you don't get this features you want to have. So at some like Nordlund, Tobias Brandenburg and Peter Capelli have shown recently that the flux tube model is not that good. So you have to think about alternatives, because turbulence can kind of destroy the flux tubes, and also you've seen in some simulation that magnetic fields is going pumped down back to the convection zone. And here also some simulation recently from a group in Oslo. They're like one group who really looks at their much more higher up, like in the going to the chromosphere and in the corona. So what they do, they have like a whole model which includes the corona, and then they have a flux tube which is like in the convectionals and let them rise and look what happens. So
what are you plotting there? What are you showing there?
So this is the magnetic field
intensity.
lines.
I mean, is it in intensity, magnetic field, temperature?
This is the red curves here as magnetic field lines, which is the initial magnetic field. Here you have, this is temperature, and here you see also some slides as temperature and photosphere. So like the motivation for the paper was like to get a model where you have like forced create forced turbulent large-scale dynamos to get a twist magnetic field, and to a bit like try to study alternative to the flux tube model, and also for when you study dynamos, it's always important what boundary condition you use, because the boundary conditions are very important to the how the dynamo works and how much magnetic field will build up. So so it's also a study like looking at the force-free boundary condition at the dynamo dynamic model. So my model, my simulation is the 3D MHD box simulation with the pencil code. You have a 2-layer system, which is kind of separated by an error function. And so error function in some in the equations. The boundary conditions are an x and y periodic for all quantities, and the velocity at the top and the bottom are stress-free, and magnetic field at the bottom is a perfect conductor, and at the top is a vertical field. Okay, coming to the equations. So on the lower layer, which will kind of somehow represent the convection zone without convection, I solved the induction equation, the continuum equation. H is it's should probably have wrote this. H is depends on the density, so you can also write this in terms of density. And the momentum equation, the important thing is that you get here forcing in the momentum equation. H is the let's call it the enthalpy, not the real enthalpy, but kind of enthalpy.
It's, yes, sound speed squared times logarithmic density.
Yeah.
It reduces, of course, to the regular enthalpy for gammas different from 1.
It's density and something.
Okay, yeah, the important thing is that you hear the forcing. So I forced with helical transversal plane waves to get force turbulence, and then you can rule that magnetic field. Okay, this is the Lorentz force. In the upper layer, which is kind of representing the chromosphere and the corona, and you have the same induction equation, but you don't solve the continuity equation, and in the momentum equation you don't have the force term. And like in the code, the equations are like bound with the error function, so you can use this equation. So thing is, what I use in the upper layer is a force-free approximation, so you don't have here any pressure gradient and any temperature. Yeah, pressure gradient and temperature and no gravity. So it's like a simplified model, and this is called force-free approximation, which you can find, or is like written here in this book. And here is this 2D simulation with a force-free, where you can have some. So this is magnetic field lines, and you can also kind of eject something up in the corona, which kinds of makes the force-free model also a good model for like things I want to observe. For.
There's no gravity at all here.
Yes.
It's gone.
Yes. And yeah, and the thing is like was also why I do the simulation is to get like bits, or to investigate like flares and CMEs, and this is kind of the first step. And here you see that you can get with force-free model also some ejection of magnetic field. And this is what I have done in my master thesis. Here you can see they also use a force-free approximation for the corona, and there you see the red curve is the magnetic field lines, so you get some kind of shape as in the corona, and so yeah, you can kind of use the force-free approximation for our model. Come to the results. You get a magnetic field which was raised up. So you put in a Gaussian randomly distributed magnetic field. Then you then it will very shortly go down, and then will build up again to like this kind of value. So it's about 10% of the equipotential value. And yeah, and what you see is that you get in the first part exponential growth, and then you get a saturation. So and this really means that there's a dynamo working on. If you don't have a dynamo, it also wouldn't go up and would go down afterwards because of the diffusion. Then when I look at the field structure, you get a large-scale field, which you see here in the BZ direction. So these are like the two layers. And here is the plotted the BZ component on the surface of the layer. And here you see you get a large-scale field, which is kind of surprising. And then you get this arcade-like structures from because of the BZ component and the vertical field boundary condition. And what you see, maybe it's not that good to see in this picture, but they also have some helical shape. So it's also very important when you look at flux emerge, how magnetic fields, when you look in the surface, they always are kind of helical, especially when you look at flares.
Arcade means like arches, or?
Yeah, like. So when you look then like on the slide in BZ, you see here's the surface, you see the variation, so you get the very large scale variation in the y direction. And when you then use Fourier method to really look how they are like the frequency or the difference, or what to say, the change of the magnetic field is, you see that you have an BZ very like here peak. So this is for the O1 component, which means like a K vector which is going in the y direction. So there you see you have a large scale field.
So
sorry, the z direction is presumably perpendicular to your two boxes.
Yeah, this is the z direction.
Okay, and the x and the y, that's sort of.
The y is here in this direction, and the x is it's a slide in x.
Ah, okay.
And
Can I ask about the
Yeah.
previous slide? The previous one?
yes,
The magnetic field configuration you get there.
yes.
How much of this is determined by the upper boundary condition that we have free vertical? Isn't this nearly force the kind of structure you get?
Yeah, kind of. So the vertical field boundary condition is kind of the trigger to get kind of the structure. Is right. So when you use other kind of boundary condition, you will don't get like this shape. So you get more like loop structures. Also depends what kind of boundary condition you use. But yeah, so it's always the thing what is a suitable boundary condition for this problem. So for the sun, I think it's not that clear because you have kind of both. You have like closed loops, and you also have vertical field.
I think that in the common field you may have a field which sort of bends over and plays for very long distance near a horizontal.
But in your case, you have a wind, and so that actually, you come to that I think later. But that will blow open any closed structures, or it will try to blow them open.
Right, but that is not proven by simulation.
It is like, you have a wind at least in simulation.
Yeah.
I mean, whether it really how much it has an effect, you have not shown yet.
But I mean, it is guided by the
The wind not. The wind comes from the magnetic field.
Right. But if you had another boundary condition, you would not have allowed the wind.
Are you consuming energy that is
No.
sort of the dark after 1,000 years of simulation, or are you feeding it with energy?
The thing is, I don't solve any energy equation in this model.
It's just there.
You have a forcing
Otherwise
function.
you would consume.
You can think about energy as like you have forcing. So you put in forcing is the input energy.
Maybe you should show from the equation again, which the turbulence is driven. That's what it's.
Yeah.
And in reality, it would be convection, of course.
Okay. And the other thing is, which is of course, you mentioned forced by the boundary condition, but you get something like X point here. So you get there when you plot the current. This is the pink one is the current. You get like strong current sheet layer, which is kind of important when you look at CMEs flares, that that you need like high energy accumulation there to get to free this energy to inject the plasma. Okay, then I look at how really the upper layer is force free. So I look at the current density and the magnetic field, and using this equation and to determine if is J parallel or anti-parallel to B, or is J has a certain angle to B. So and here's the plotted the normalized value of G dot B and here G cross B, and you see, which means that when it's parallel, the G cross B is 0 and G dot B is the maximum. And you see something like this, that you have highly parallel structure here, or highly structured. You have they're highly parallelized magnetic field and current density. Here you see at the end, this comes from the current sheet I have mentioned before. And here also you can plot the angle, which is which you see here is the turbulent layer, which is there, kind of pi half, and here goes to pi. Then I compare my simulation with a mean field model. So just solving this equation. So the thing is, the mean field model is one model to describe like a dynamo, and so you have an alpha here, which is kind of the strength of the dynamo on the turbulent ether. And to get the mean field model right, I also use the error function for alpha, so that you have an alpha in the lower part and in the upper part no alpha. And I choose these parameters where I put them U, S from the simulation. And then I compare this, and you get very similar shapes. So it means this kind of the simulation is consistent with the mean field model, which is kind of important for the dynamo.
But you take URMS from the direct simulation.
Mm-hmm.
Isn't that consistent with the assumption that alpha is 0 in the upper layer?
Mm-hmm.
Because in the upper layer there is a URMS, isn't it?
Yeah.
But you said before that alpha in the upper layer is 0. Do you take it from only from the lower layer? Only from the lower layer, maybe?
Yeah, but the lower layer is like the URMS in the lower layer is nearly the same value as the URMS in the same in the whole area.
No, I think
When
you're
you take
asking. I think you're asking how much does it actually drop, the URMS, and I think it drops by quite a bit.
Yeah.
So it is not bad to assume that alpha really goes to 0 in the.
But if you do it technically, like described, that URMS is taken from direct simulation, then alpha is not 0 in the upper layer.
Yeah.
But it's very
That's
small.
right. The thing is,
Okay.
we just so it's like the idea was like, okay, you produce a dynamo here because of the forcing, so you want to produce a dynamo here because of the alpha effect, and to get dynamo production in the upper layer. So you use for the alpha the error function. For the URMS you use the value of the root, which is kind of the same as the on the upper part, lower part. Yeah, what you also see is a upward wind, acceleration, and so he has plotted there the z value and like the velocity going in the z direction, and you see that in the lower you basically nothing, but in the upper layer you have like high velocity and they go always higher, so you get a wind which is which go to the upper layer and increase by time. So this is several time steps. Yeah, and this also, when you compare, when you go back, this also may be a conclusion that you have some of these difference because you don't have an upper wind in the mean field model because you don't really solve momentum equation. So this may be a conclusion for the difference. Okay, coming to the conclusions. So I can, with my model, I can create a dynamo by forced turbulence, and the magnetic field grows exponentially and then saturates. You get a large-scale field in the BZ. When you look at their y direction, it's kind of a sinus shape, and their magnetic field lines forming helical arc-like structures. And I tested also this the force-free assumption kind of good, and they're consistent with simulation. And and the mean field model is also consistent with the simulation. And like as a big conclusion, it kind of show that the dynamo can create twist magnetic fields below the surface, and this can emerge, and this looks to get some similar things like large-scale fields or something like this. Outline. One thing is we could investigate much further is like how does magnetic fluxes depends on the Reynolds number. So using different simulation with different Reynolds number, and how does really influence the simulation into elasticity fluxes. Then one thing is to include shear to the model and look what then happens. And one important thing is looking at the global geometry, that with curvature, and also include gravity to get a bit more realistic to the sun. And other thing is like using convection, so you having a real convection zone instead of forcing. And the other thing we can also think of, like now we use a force-free approximation in the upper part. We can think about using a full MHD model. I mean, like using temperature, using energy equation, cooling, and all different stuff. But this means like the problem would be more complex, but also and you take much more computing power to do it. And we can have to decide is like makes sense to do it or. This was.
I missed the beginning, but I'm assuming that from hearing anyway. It's trying to guide people in. So, questions?
Again about gravity.
Mm-hmm.
If you don't have any gravity, you don't have any specification.
Mm-hmm.
And then there's something which distinguishes up from down. Is there? So why does the field emerge up but not down, for example?
No, because you have in the upper part forcing, and I think the forcing will drive it up.
Okay.
So this is like, I would say so.
Because when people have done these emerging flux simulations without the dynamo, then of course the gravity defines through buoyancy which direction the flux goes.
Yeah, and they also have a density stratification.
Yeah, you get that automatically by putting in gravity.
Yeah, sure.
So is it the model you're saying, because the way where you put the dynamo, or is it the boundary condition, or what is it that prevents flux from?
I would say like this like the dynamo in the upper part, and I have to think about boundaries.
What was the lower boundary?
For the magnetic field, this was perfectly mapped.
I think the reason is really that you have an active region and a not active region. So it's natural to have a flux therefore from the active region into the non-active region. It's like you have a hot block of copper, and you ask the question, where does the heat go? Of course, it goes simply away, regardless of the notion of up and down.
So it's a sort of symmetry broken in the model itself.
Yes.
And you also get a upwind, which can sort of drive.
I think one should also realize that the field that is being driven by the dynamo is strongly twisted, and the twist wants to get out. So it's and that's something which I think is quite important for our model, and this has never been considered by any other group, of course, because they have always been relying on gravity alone as being the main. I mean, buoyancy force is as a main agent which brings the magnetic field to the surface, for example. Here it's not at all the case, and yet it looks quite promising.
Well, I'm mostly observer, and I was trying to see what are actually the magnitudes that you are working with magnetic field here. I mean, you have all these nice plots with 3D with vapor, but I don't see any scale of what you're showing, so
I can...
It's very hard to get an idea of what are the magnitudes of...
Well, if I want, I can just look up the values, but I don't now know by heart. But the thing is, for this thing, the value wasn't that important. So we just look at structures and to look at relative values.
But you could look at your plot of the overall field strength. That was.
I mean, you have the
10%
but
of
0.2 watt. Is it Gauss? Is it kilograms?
And this is
yes, that one.
this. So this is nominated by the equipartition ring,
Which is
which is
It must be on the order of 1,000 Gauss or 300 Gauss. It's less than the sunspot field. So that would
so
be.
it was not the issue really to to get values that you really compare it with observations. We just focus more on the structure, the mechanism.
So I think it would mean the mean field, large scale field in the corona or in the outer part would be on the order of anywhere between 10 to 30 Gauss. Not terribly. What do you think about that? Would that make sense?
No, the corona, I have no idea. In the chromosphere, I would say you usually get. I mean, the photosphere you can get how much in the white sun? 200 Gauss, maybe 200 Gauss concentrations.
200?
Yeah, in sunspot, of course.
In sunspot regions, right. Yeah, this is now averaged over the entire domain.
What?
I mean, this is an averaged field, of course, as defined by the equation here.
Yeah.
So if you're comparing against observations where you look at the peak fields, then they would probably be more of the equipartition value, which then is indeed a few hundred Gauss. Equipartition with respect to the photosphere.
Well, yeah, I'm a bit lost as an observer. What would the density and temperature look like as a function of Z?
The temperature is has a certain value which we don't have to care about because we don't solve the equation. So it's constant for the whole Z component. And the density is I don't have the plot here, but the plot is in the paper. It's initial density is constant, and it will because of the forcing and the kind of lower layer and the error function, it will go down a bit in the lower part, but just a little bit.
Okay, I mean, why would then the corona look like corona if it has low temperature and high density?
Because it's a simplified model, so you can't. The thing is, you can, if you want to model like a corona or something, you can't really start with using every equation, which is very realistic. And so you have to simplify some things to get the computing time shorter, or you always have to think what you wanted to observe. If you want to observe magnetic structures, then sometimes it's enough to use just the force-free approximation without energy field. But if you want to look at radiation fields, coronal heating, all the stuff, then you have to look. Then you have to complete the simulation with some cooling, radiation function, energy function. Yes.
okay. Well, very last question.
Regarding what you just said, you have to be careful with that because you have an equilibrium between the environment and the flux tube. Otherwise, it will expand. Well, yeah, I mean, you have some kind of flux tube there, I guess. You said two, have a bipolar region, right?
No.
You have two things there.
Yeah, it's like two.
Well,
two
anyway.
strings more. Yeah.
But you cannot just assume that the structures that you have seen are realistic based on not having, because I mean you can say, okay, I want to observe the magnetic field, so I remove everything else. But everything else will actually get in equilibrium with that. That's what you have. That's why you observe flux tubes in the sun, because it actually is in equilibrium with the environment.
No, I wouldn't say it's like you can like take all the results there and say this is like this, but you can always. It's always a good way to kind of simplify it first, and then to make some modulation, and then sure you always get different. Also, when I what I do in my master thesis, also assume force-free approximation. There you see also some features which you don't, or some structure you don't really see in a whole corona simulation. But you get something which is kind of similar in which way. You always have to. You're right. You always have to be careful.
I mean, the sun is also not a real equilibrium. It's just a dynamic equilibrium. Things are changing. Sunspots don't live forever. And the same is true here. You get structure self-consistently out from the dynamo. Regarding your earlier question, maybe one should emphasize: if you put everything in, then one would not be able to argue what was really important. Was it gravity which was important, which was perhaps the predominant paradigm? Or is gravity not important? And if gravity is not important, you can only show that in a simulation where you don't have gravity. And in this case, we do see effects.
Was that the motivation for using gravity?
Yeah. So I would say you always get like have first a simplified model, and then if you like kind of understand this and kind of interpret the results, then you can always add more, and then you can see the difference. And also,
I guess the danger there is that you could have cancelling effects, right? So if you leave out gravity and, I don't know. You leave out gravity and temperature and the energy equation, then somehow you get a model that works, and then you put in gravity, you don't do the energy equation, it doesn't work at all.
Yeah.
That's, I guess, the building blocks don't necessarily are progressive in that sense.
I think that's right, and therefore we need the spherical geometry at the same time. So you have to really make the cancellation effects correct, of course. So once you put in stratification, I think it's important to have the spherical geometry, because that allows you something like a wind again to go really away from the sun. It would not come back then.
I guess we never look at this. If there are more questions, Jörn is around for another 4 years or so. As we normally say with seminar speakers, that they're around for the rest of the afternoon. Okay, so thanks very much.